popular units, of measuring strength of different aqueous solutions. Units of measuring strength of different solutions, which I already told you. Could be an aqueous solution of an acid, base, salt, oxidizing agent, reducing agent, and we'll begin with the most popular of them, which is molarity. See, if any of you could define molarity, how do you define molarity? Anyone who could define molarity?
Also, number of moles of solute per liter of the solution.
Exactly. You know, we're going to define molarity as number of moles of solute per liter of solution. Now, used to terms like solution, solute, solvent. Solution is going to be a homogeneous mixture, you know that. We'll have components, solute and solvent. Now, what's your idea about a solute? What do you mean by a solute? Tell me. What do you mean by a solute?
The substance which is present in less amount in a solution.
Exactly. That's again the ideal way of defining a solute. Chances are so many times till class 10 our perception towards solute and solvent is something which gets dissolved. Something which gets dissolved is the solute. And you know, we are expecting it to be a solid particle most of the times, and something which acting as a medium is dissolving solute is supposed to be a solvent. Yes or no? And then you expect a homogeneous mixture which will be called a solution. Now realize this limitation of you know, defining a solute as something gets dissolved and a solvent as the medium which is dissolving the solute will come up with a serious limitation when we move to mixing two liquids. Suppose we are mixing two liquids and it's two miscible liquids, it's hard to say which is getting dissolved in which. Alright, if it's about mixing two gaseous compounds, two gaseous elements, mixing oxygen and nitrogen. So a more fair way of defining solute and solvent is going to be generally the one which is smaller in content will be called the solute, and the one which is more in content will be the solvent. That together constitute the solution. Now moving on, almost every time in our discussion water will be the solvent because we will be preparing aqueous solution of various chemicals. I hope I am very clear about it. Almost every time we will be dealing with aqueous solution of various chemicals. So those chemicals would almost every time act as the solute, and water would be the solvent. Water is going to be the universal solvent, and the number of moles of that solute, be it an acid, base, salt or any chemical compound, per liter of the solution will be defined as the molarity of that substance. So very quickly, suppose we are talking of a chemical compound. We are talking of a chemical compound having molecular weight m, and if you dissolve say W grams of it, you dissolve W grams of this and form V liters of the solution. So certainly W by m, weight upon molecular weight will be the number of moles, weight by molecular weight will be the number of moles. Yes or no? I repeat, if you dissolve W grams of a chemical stuff and get V liters of a solution, so W by m will be the number of moles upon V in liters. So this will give you molarity. Number of moles per liter will be the molarity of the solution. Got me? I repeat, if you dissolve W grams of something having molecular weight m, W by m, weight upon molecular weight will be the number of moles of that solute upon total volume will tell you number of moles per liter. That will be the molarity. We will want to define molarity this way. But we will apply molarity differently. Believe me, again, you know, practically in the laboratory or in course of problem solving, chances are we will be dealing with volume in ml more often. Small little test tubes will not hold liters of solution. So in a test tube which is going to hold a few ml of a given solution, realistically almost every time the volume given would be in ml. I repeat, it's not incidental that most of the problem solving would be over data, you know, where the volume will be in ml, because almost every time, you know, carrying out chemical reactions, small little test tubes will be working with volume in ml. So we are going to define molarity this way, but we are going to apply molarity differently. We realize instead of the volume in liter, if it's given in ml. But to progress, I guess this is understood by all of you. Molarity of a solution will be number of moles per liter of the solution. Now say the volume in ml is given. If the volume in ml is given, you will want to divide it by 1000, and then it's going to be a multiplicity factor in the numerator. Yes or no? So you want to know it as number of moles of solute per liter of the solution. Number of moles of solute per liter of the solution, and because almost every time I repeat the volume will be given in ml, you will want to apply it as number of moles into 1000 upon volume given in ml. So molarity is going to be number of moles per liter or number of moles per ml into 1000. Yes or no? Because I repeat almost every time the volume will be given in ml, and this is where I am going to define a different term. The way number of meters into 1000 gives me number of millimeters. Number of liters into 1000 gives me number of milliliters. I will define a term where number of moles into 1000, and I will start calling it number of millimoles. I will start calling it number of millimoles, where I will conceive millimole as 1/1000th of a mole. I will conceive millimole as 1/1000th of a mole. Yes or no? You guys look less convinced. I repeat, molarity will be defined as number of moles per liter. Molarity will be defined as number of moles per liter, but will be applied as number of millimoles per ml, because I repeat almost every time the volume will be working with will be in ml. Now the way ml is 1000th of a liter, you will want to think of a millimole, which is 1000th of a mole, and then it would be easier to digest that it doesn't matter whether it's number of moles per liter or number of millimoles per ml. Number of moles per liter or number of millimoles per ml. Got me? And certainly I've tried to explain it to you. If you have volume in ml, you'll want to divide by 1000. This is going to go in the numerator, and number of moles into 1000 would certainly give you number of millimoles. Fair enough? Somewhere out here, I'm going to write molarity as number of moles by volume in liters or number of millimoles by volume in ml. I repeat, it will be defined as number of moles per liter, but will be applied as number of millimoles per ml. Number of moles per liter, but will be applied as number of millimoles per ml. The way ml is 1000th of a liter, we will want to think of a millimole, which is the 1000th part of 1 mole. Got me? And then your understanding is going to grow with the application. After molarity, the second very popular and in terms of problem solving even more significant would be normality. Now who will define normality for me? Normality will be defined as? Exactly. Normality of a solution will be defined as, take down number of equivalents of solute, number of equivalents of solute per liter of the solution. Number of equivalents of the solute, number of equivalents of the solute per liter of the solution. The solution, per liter of the solution. And see if you find it hard to understand. The way number of moles was weight upon molecular weight, number of equivalents will be weight upon equivalent weight. Number of equivalents will be weight upon equivalent weight. One equivalent of oxygen is 8 grams. So 80 grams is 10 equivalents. Yes or no? And normality being number of equivalents per liter, yet again if you're dissolving W grams of solute and form V liter of the solution, you're dissolving W grams of something, jiska equivalent weight is capital E. Now W by E will give you number of equivalents, W by E will give you number of equivalents. Now this in V liters of the solution, so upon VL will be number of equivalents per liter, will be number of equivalents per liter, yes or no? Yes, and yet again we face the same situation where if the volume is given in ml almost every time, you'll want to divide by 1000 and this going in the numerator. You'll want to define normality as number of equivalents per liter, but you're going to apply normality as number of milli equivalents per ml. It's going to be applied as number of milli equivalents per ml. Normality will be defined as number of equivalents per liter of the solution, number of equivalents per liter of the solution, but will be applied as number of milli equivalents per ml of the solution. All right. And yet again your comfort level is going to grow with a few applications, but so far you're supposed to buy all of it. So you've been following me. And yet again somewhere I'm going to write all of it again. Normality will be defined as number of equivalents per liter of the solution. So if you formed 3 liters of the solution, number of equivalents upon 3 will give you number of equivalents per liter. That will be the normality. All right. And it's going to be applied as number of milli equivalents per ml. Number of milli equivalents per ml. Now moving on. Realize if this capital M was W by M upon VL, and if the normality is W by E upon VML, I don't want you people to get confused between this capital N and this capital M. So maybe I'll call it M prime, or rather I'll call this M prime. Capital M, let capital M be molecular weight only, and for molarity I'll be using M prime. All right. Now for the same solute, in the same solution, how do you relate normality and molarity? How do you relate normality and molarity? Now one look and you realize that normality is going to be equal to molarity. Maybe I'll want to be more elaborate here. Normality will be equal to molarity into molecular weight upon equivalent weight. Alright, look at the two expressions, this giving you molarity, that's giving you normality. You'll find normality will be equal to molarity into molecular weight upon equivalent weight. Got me? And if you again recall that we were obtaining equivalent weight as molecular weight of the acid upon the basicity, molecular weight of the base upon acidity, molecular weight of an oxidizing or reducing agent upon change in oxidation number, and whatever used to feature in the denominator was my n factor. So m by E will be the n factor, m by E will be equal to the n factor. We are reducing equivalent weight as molecular weight upon something in the denominator, and that used to be the n factor. So certainly the ratio m by E, has to be the n factor. Yes or no?
Yes, sir.
And let's agree, then normality will be equal to molarity into n factor. Normality will be equal to molarity into n factor. The first concept I impart to you about n factor is, it will tell you number of equivalents per mole. If you remember, I was very particular about that particular statement, I was very particular about that statement. That n factor will tell you number of equivalents per mole. It will tell you number of equivalents per mole. And maybe, instead of theoretically talking more of n factor. Very quickly, let me give you a couple of examples. Say you have 196 gram of sulfuric acid in 2 liter solution. You have 2 liter solution in which you have dissolved 196 gram of sulfuric acid. What's the molecular weight of sulfuric acid?
98.
Molecular weight of sulfuric acid is 98. What's the equivalent weight of sulfuric acid?
49.
49. Because you realize n factor for sulfuric acid is 2. N factor for sulfuric acid is 2. Yes or no?
Yes, sir.
This being dibasic, n factor is 2. So molecular weight is 98 and equivalent weight is 49. Now let's quickly look at the molarity of this solution. Weight upon molecular weight upon volume in liters. So that's going to be 1 molar. The solution is 1 molar. 196 grams is 2 moles in 2 liters. 1 mole per liter, and the molarity is 1 molar. Normality, weight upon equivalent weight, which is 49 upon volume in liters 2, and see, it's going to be 2 normal. It's going to be 2 normal. Yes or no?
Yes, sir.
So normality is 2 because it's 2 equivalents per liter, or primarily it's 4 equivalents in 2 liters. It's 4 equivalents in 2 liters. So 2 equivalents per liter will make it 2 normal. 2 equivalents per liter will make it 2 normal. 2 moles in 2 liters. So 1 mole per liter will make it 1 molar. Yes or no? So the same solution is 1 molar or 2 normal. The same solution is 1 molar or 2 normal. Yes or no? So normality is molarity into 2. Normality is molarity into 2. Normality is molarity into 2. Believe me, I am not up to giving you a bunch of results, and I'll not want you people to be dependent upon all the results which I am framing for you. These are only directions in which I'm trying to drive your mind. These would help. These statements would help. But over a period of time, all of this should flow instinctively. Certainly, you will need some time to get used to these units. But I repeat, n factor has to be considered as number of equivalents per mole. Number of equivalents per mole. And number of equivalents any day will be equal to number of moles into n factor. Yes or no? अरे बाबा n factor will tell you 1 मोल में कितना equivalent है. n factor will tell you 1 मोल में कितना equivalent है. n factor will tell you how many equivalents per mole. So if this is the number of moles, into n factor will tell you number of equivalents in these number of moles. N factor will tell you number of equivalents per mole. So n is the number of equivalents per mole. If this is the number of moles, into n will tell you number of equivalents in these number of moles. Yes or no?
Yes, sir.
These number of moles per liter will give you molarity, and these number of equivalents per liter will give you normality. So any day normality should be equal to molarity into n factor. Normality should be equal to molarity into n factor. And as you could see here, you have 1 mole per liter, making it 1 molar, and 2 equivalents per liter, making it 2 liter, 2 normal. Yes or no? And basically, if n factor is 2, what you start believing is, and by this time, you'd have kind of accepted n factor 2 will mean equivalent weight is half of molecular weight, and 1 mole is 2 equivalents. 1 mole is 2 equivalents. 1 mole is 2 equivalents. So the number of equivalents will always be twice the number of moles, and normality will always be twice the molarity. Yes or no? And only if I'm able to drive this thought into you using a simple illustration of this kind, I'll want the people to buy henceforth the cases which we did in the past, with more popular reagents, KMnO4, K2Cr2O7. I'll want the people, to start accepting maybe one more time KMnO4 in acidic medium was becoming Mn plus 2, and n factor was 5. In alkaline medium, n factor was 3. I'm really sorry, I've just made a small mistake here. I'm the one who constantly tells you we'll want to note it in order: acidic, then neutral, then alkaline. I'm sorry about it. KMnO4 plus 6 plus 4 here. Guess you could understand all of it. In fact, it was 5, 3 and 1 in acidic, neutral and alkaline medium, making equivalent weight m by 5, equivalent weight m by 3 and m by 1 respectively in acidic, neutral or alkaline medium. Yes or no? Yes or no? We did it before. Depending upon the medium, equivalent weight will be m by 5, m by 3 or m by 1 in acidic, neutral or alkaline medium respectively. You got to understand molecular weight will be constant. Molecular weight will be constant. So किसी भी solution का molarity will be constant. For a solution, molarity will be constant because molecular weight is a constant and number of moles will be constant. Equivalent weight is variable. Equivalent weight is variable, and so would be number of equivalents, so would be number of equivalents, and so would be the normality. Molecular weight will be a constant, so molarity of a solution will be constant, and then depending upon the medium, depending upon the change, depending upon the nature of the chemical reaction, normality could be defined. Equivalent weight will be variable, number of equivalents will be variable, molarity will be constant, but normality will be changing. Yes or no? Depending upon the n factor. Now I did tell you that it's not incidental. Most of the times we'll end up working with KMnO4 in acidic medium. You'll find KMnO4 being used with sulfuric acid or HCl because in acidic medium the n factor will be maximum. N factor will be maximum, and you guys understand it's about plus 7 becoming plus 2, taking in maximum number of electrons. Here it's taking 5 electrons per mole. Yes or no? So it's acting most effectively as the oxidizing agent in acidic medium. Now what I want you to buy now is, suppose you have a solution of KMnO4 which is 2 molar. If there is a solution of KMnO4 which you know is 2 molar solution, molarity will be constant. This means 2 moles per liter. A 2 molar solution will mean 2 moles per liter. I want you to understand in acidic medium 2 molar will be the same as 10 normal. 2 molar will be considered 10 normal in acidic medium. Hey, n factor is 5. N factor is 5. So 1 mole will mean 5 equivalents. 2 moles will mean 10 equivalents. Is it that hard to believe? 2 molar matlab 2 moles per liter. 2 moles per liter. N factor 5 would mean 1 mole has 5 equivalents, 2 moles have 10 equivalents. So 2 moles per liter is the same as 10 equivalents per liter. So 2 molar will be 10 normal, 2 molar will be 10 normal, and I repeat in future you'll want to instinctively convert molarity to normality, believing the unit in normality will be molarity into n factor. If the medium is neutral, a 2 molar solution would be 6 normal. If the medium is alkaline, then 2 molar will remain 2 normal. 2 molar will remain 2 normal. Yes or no? In alkaline medium, equivalent weight is the same as the molecular weight. In alkaline medium, equivalent weight is the same as the molecular weight. Certainly, number of moles and number of equivalents will be equal, and normality and molarity will be equal. Yes or no? Tell me about K2Cr2O7. What was the n factor for K2Cr2O7? None of you are doing your job all right, believe me. If you have to turn around pages and recall this, and still if you come up with the wrong answer, that's not going to excite me. And if you find it funny too. Well, Keep on telling you, everything which I put up on the whiteboard has to be significant. You're having your vacations right now, something which we discussed a couple of days back. If you're not able to relate to it right now, 3 for 1 chromium atom, 6 for 2 chromium atoms. 6 for 2 chromium atoms. And I did work it out in a very detailed manner, I remember. Molecular weight was 294 and equivalent weight was molecular weight upon 6. Yes or no? Plus 6 to plus 3. For 1 chromium it was 3 units, for 2 chromium it was 6 units. Yes or no? So we agreed that equivalent weight will be molecular weight upon 6, equivalent weight will be molecular weight upon 6, n factor will be 6 here.
Yes.
Which means 1 mole has 6 equivalents, 1 mole has 6 equivalents. So for K2Cr2O7, if I present you a 2 molar solution, this would not be very bothering if I tell you it's the same as 12 normal. 2 molar solution of K2Cr2O7 will be a 12 normal solution. And this is where instinctively you will want to relate molarity with normality and vice versa. Okay? And this would hold true for the rest of the cases which we did in the past or situations which will come across. Normality will be equal to molarity into n factor. Yes, I can grab all of it. Now, I mean, all of this in first few classes of physical chemistry would mean so much. Normality is going to be equal to molarity into n factor. By now n factor tells you number of equivalents per mole. N factor is basically the ratio of molecular weight upon equivalent weight. This will always hold true. Normality will be equal to molarity into n factor. Molarity will be a constant because molecular weight will be a constant. If depending upon situation n factor is variable, normality will be variable. We'll see the application front very shortly, but before that you'll want these to be completely ensconced. What we also get from the couple of expressions I wrote there is, and this would be meaningful. I'll certainly make you understand. Number of millimoles will be equal to molarity into volume in ml, and number of milliequivalents will be equal to normality into volume in ml. You know what I am doing? Using those two expressions, you find, again you will want to know number of moles is molarity into volume in liters. Maybe I don't mind writing a couple of more expressions for you. Number of moles will be equal to molarity into volume in liters. So I'm just performing a cross multiplication. So number of moles, if both molarity and volume is known to you, if they wanted to find number of moles of sulfuric acid in 5 liters of 2 molar solution, got me? So number of moles will be molarity into volume in liters. Number of equivalents will be normality into volume in liters. Number of moles will be molarity into volume in liters. Number of equivalents will be normality into volume in liters. Alright. You will want to know this, but chances are yet again we will be applying this more often because the volume will be given generally in ml and we will be dealing with millimoles and milliequivalents more often than moles or equivalents. Got me? And certainly I am going to display the application in front of all of it. For the time being, I will want you people to have taken a good note of this. Later on we'll need these expressions like anything. Number of milliequivalents is equal to normality into volume in ml. Maybe not at this point of time. I'll be again pretty curious to know how many of you have got started with normality and molarity in school. Completed. Chances are even the rest of you at some point of chemical arithmetic, maybe after the vacations get over, will have to deal with these terms.